Today we are going to discuss relative hydrolysis. So please give heading relative hydrolysis of haloalkanes and acyl chlorides. Relative hydrolysis. Previously we compared the relative acidities and basicities. Today we are going to compare the relative hydrolysis. So please give the heading relative hydrolysis of haloalkane, acyl chlorides, and chlorobenzene. Relative hydrolysis of haloalkanes, acyl chlorides, and chlorobenzene. Acyl chlorides, chlorobenzene. Now, first let me explain, then I'll let you write all this. So first, please let me explain this. First, you need to understand what is the hydrolysis. Please pay attention. In hydrolysis, for example, if this is a haloalkane, okay, this is an acyl chloride, okay, and if I compare these two, the hydrolysis is when they react with sodium hydroxide aqueous. It's OH negative, comes in and takes the place of this Cl, replaces this Cl, in other words. Okay, and what is the product formed? The product is RCOH plus Cl negative in this case. In this case, again, RCO and then OH plus Cl negative. So you see what happened in both these cases. It attacks this carbon and there is a substitution of Cl. Am I right? Yeah. Is it so? Now, what happens if somebody asks me, or if I can take, here is the, if I take it to the next level, here is the benzene and then Cl. And similarly, OH negative comes and takes the place of this, attacks this carbon and substitutes this. So hydrolysis, I hope you understand, is the replacement of Cl. The halogen of haloalkane, this is the first one is what? It's a haloalkane. The second one is what? It is acyl chlorides. And the third one is what? Chlorobenzene. Right? So it's a substitution of Cl in all these cases by the OH. Okay? Now, obviously, if it is coming to substitute, the strength of this bond matters. Which bond? CCl. CCl and CCl. If I start with haloalkane, this is partial negative, this is partial positive. This CCl bond is of normal strength. The OH comes in and takes the place or substitutes this Cl when you heat it. On the other hand, in COCl, we have learned in the previous section when we were doing the relative acidities and basicities that CO, because of high electronegativity of oxygen, acts as what? Electron withdrawing group. When it acts as electron withdrawing group, it pulls the electrons towards itself. This CCl bond becomes what? Weaker. This CCl bond is way, way weaker than the CCl bond of this haloalkane. Therefore, when you undergo the hydrolysis of acyl chloride, you don't need any heat. Even the cold water, you don't need sodium hydroxide. You just add cold water, and even the reaction is very fast and vigorous because it has turned this CCl bond weakest out of haloalkane and acyl chlorides. On the other hand, if you look at the chlorobenzene, you use cold water, no substitution takes place. You use sodium hydroxide aqueous, no substitution. Even if you heat it, no substitution. Why? Because we remember we said that yes, due to the chlorine lone pair of electron pass towards the benzene ring, known as mesomeric effect, this CCl bond is way stronger, behaves like more or less like a double bond. So this OH cannot substitute. So I hope you understand what I'm trying to say. In hydrolysis, we have to see the strength of what? CCl bond, and then we have to relate the rate of hydrolysis. The weaker CCl bond mean more hydrolysis. This, yeah, I'm doing it. So what I'm saying, in acyl chloride or any other hydrolysis, you have to focus this. Okay, what about the strength of CCl bond? If the CCl bond is stronger, hydrolysis is hard. If CCl bond is weaker, the hydrolysis is easy. Right? How this CCl bond become weaker if you put C double bond O here? So it's going to weak this bond. And how this is going to become stronger if you put benzene ring next to this? So what I'm saying is like this, that this is CCl bond. If I put benzene ring next to this here, C6H5 and then Cl, so what is going to do? It's going to make this bond stronger. If I put C double bond O next to Cl, what is going to do? This CCl bond weaker, and this is in the middle. So haloalkane slower than acyl chloride in hydrolysis or in the rate of hydrolysis, but faster than benzene, chlorobenzene, right? Okay, now I'm letting you write all this. So please write down. Hydrolysis depends on the strength of CCl bond. Hydrolysis depends on the CCl bond. In acyl chloride, CO acts as electron withdrawing group, so pulls electron density towards itself, making CCl bond weaker. Hence, increasing ease of hydrolysis. So they asked you, acyl chlorides are more in hydrolysis or faster in hydrolysis than haloalkanes? You say yes. Why? Because CO acts as electron withdrawing group, pulls the electrons towards itself, making CCl bond weaker, hence increasing the ease of hydrolysis. In acyl chloride, I'm dictating C double bond O acts as electron withdrawing group, so pulls electron density towards itself, making CCl bond weaker, hence increasing ease of hydrolysis. नीचे लिखेंगे in haloalkanes, the alkyl group is EDG, has a positive inductive effect, making CCl bond stronger and harder to hydrolyze. Under this, you have to write in chlorobenzene, due to mesomeric effect, the CCl bond is strongest, hence chlorobenzene cannot undergo hydrolysis. वो CCl bond stronger हो जाता है when I'm explaining it. Now I'm going to give you a question here. Okay, now you have to organize CH3, CH2Cl, CH3, COBr, CH3, COCl, and C6H5Cl with the ease of hydrolysis. Hardest to hydrolyze on this side and easiest to hydrolyze on this side. Now first organize. I'll ask you, then you have to compare. I told you how to compare. You have to compare 2, 2, 2, okay? Which is the hardest to hydrolyze and which is the easiest to hydrolyze? Please first arrange them in the order from hardest to easiest, then we'll explain them. Done?
Yes.
Okay, who will tell me?
The C6H5 is the hardest. The last one.
So, okay, the hardest out of all these is chlorobenzene.
Easiest one is C3CO.
I think here you are wrong. Anyone else? The easiest, in my opinion, is CH3COBr, acyl bromide. And where is the acyl chloride then? And where is the haloalkane? Chlorobenzene के बाद CH3, CH2, Cl. And then what about the next CH3, CO, and then Cl? Okay, now let me explain this. CH3, CH2, here is the Cl. Okay, now let me explain this. If you give me the opportunity. to explain. So I'm very much hopeful that I'll be able to cover all the queries. Okay, relax, control your emotions. Okay, now why hardest? Here you are correct. Why it's hardest? Because in chlorobenzene, the lone pair of electron is passed towards the benzene ring. When it goes down towards the benzene ring, this CCl bond Aries is going to be the stronger, behaves like kind of double bond, right? So it's very much harder to substitute this. Is it right? So what we are going to write in the first one, that in chlorobenzene, due to mesomeric effect, the CCl bond is strongest, right? As compared to CH3, CH2, Cl. Okay. Now, on the other hand, now we compared these two. Now we have to do what? We have to compare these two. Why this is harder? So what you will say? Okay, in this case, it is electron donating group. So passing electron density towards itself, towards this CCl bond, making it stronger. Or in other words, you can also explain it like this. Okay, C double bond O has what? Yeah, so I think that's a better explanation. Okay, acyl chlorides contain what? C double bond O, which acts as, yes, electron withdrawing group, making CCl bond weaker. Then haloalkane or CH through CH2Cl, where CH3 or alkyl group acting as EDG, having positive inductive effect. So you can give one explanation. I'm giving you the double explanation, but you can give any one of them. Okay? Having, yeah, it's good. Positive if you have a space enough. Positive inductive effect, making CCl bond stronger and harder to hydrolyze, and relatively harder now. What about this? The last part, the last bit. Both of them have C double O, so you cannot give this explanation. Now you have to focus on one more thing. Look at this. What is that thing? This is CCl and this is what? CBr bond. And we all know that down the group, if this is fluorine, this is chlorine, this is bromine, this is iodine. If you go down the group, the atomic radius, what happens? Increases. When atomic radius increases, the bond length, what happens to bond length? Yes, so CBr bond length is more than CCl. And when bond length increases, the bond strength decreases. So CBr has a more bond length as compared to CCl. So weaker bond CBr. So it is easy to hydrolyze, right? So please write down that CBr bond length is more. No. We just have to focus on CBr bond. In hydrolysis, always focus the bond strength के ऊपर, because more bond strength, less hydrolysis. Okay, so the CBr bond length is more than CCl, making it relatively weaker. Bond, so easier to hydrolyze.
I have one more question.
Yes, go ahead.
Actually, you said that the hydrolysis depend on the strength of the CCl bond. So, sir, in the last 2 days, we are.
I mean, CCl or CBr or CI bond, obviously, when you are comparing the halogens together. So the bond which I'm focusing, I hope you understand, the halogen ka bond with carbon. So that strength matters. Okay. Now I'm going to put all these three concepts of relativity together before we go to the next section. That is, what we have done up till now is the relative acidities, relative basicities, and relative hydrolysis. For the basicity, if you remember, we focus the electron density on nitrogen atom. When it increases, becomes more basic. For the acidity, we focused on what? OH bond. When the bond is stronger, ionization is less, so it means less acidity. For this, we focused on CCl bond strength. So whenever the question comes, you have to focus on these lines and write the answers, right? So more stronger CCl bond mean less hydrolysis. More stronger OH bond mean less acidity. More stronger electron density on nitrogen mean more basicity, right? So these three things are there which you need to explain in order to have the explanation for the relative acidities and relative basicities. So chlorobenzene is almost impossible to hydrolyze. Haloalkanes, yes, they undergo hydrolysis, right? But their rate of hydrolysis is, not that much as compared to acyl chloride or acyl bromides, right? So with this, we have come to end of this. We have done with the questions, and we have also done with the relative reactivities, right? Now we are moving on to the next section, which is the polymerization. After polymerization, we have organic synthesis section where we'll be discussing the past paper questions, right? So because they are the organic synthesis in which we have to convert one functional group to another functional group, over there we'll be discussing the questions from the past paper, right? Right now, please give the heading polymerization. Okay, what is polymerization and what are the types of polymerization? We are in the last section of organic. Then we'll be left with the applications. There are three topics in applications, right? Okay, polymerization. We understand this polymerization, we are doing it since O levels. It is the process in which the small molecules called monomers add up or join to make a big molecule called polymer, right? The process.
The inorganic chemistry is on your YouTube channel.
No, not for A2, for AS. The process in which small molecules called monomers join to make big molecule called polymer. There are two types. There are two types of polymerization. Number one, addition polymerization. Number two, condensation polymerization. एक गाड़ी से उनके टेस्ट ले हैं. Number one, addition polymerization. Front seat painted. Okay, now please pay attention. Addition polymerization takes place in unsaturated compounds. Unsaturated, you understand now, which contain carbon-carbon? Double bond. Or at least triple bond, okay? So it takes place, and this takes place by the, it happens without loss or gain of any atom. Now let me explain what I'm trying to say. Listen, for example, we have these three, let's say, or four molecules of any compound. They are in a beaker. We just put a glue inside, and as a result of that glue, these four molecules join like this, right? Here they were called what? Monomers. Here they are called what? Polymers. So that's a very simplest way of doing it. That glue thing which I'm saying, it's just think of, it's a catalyst or something. I have like 4 pens. If I put in a beaker and then I put a glue, so these 4 pens, they organize themselves one after another and they make a one long chain, one long big pen having all 4 joined together like this.
What if there are two?
Okay? Is it okay?
What if there are two or three?
Yes, whatever the number is. So they keep adding up to make a polymer. Okay? So monomers add up to make a polymer. Okay? So how they add up? That's the point. For example, now let's see. This we have already done in AS. I'm just revising it here. Let's see, for example, if we have a molecule of ethene. Let's assume we have 3 molecules of ethene. This is number 1. This is number 2. And this is number 3. So what happens? When you put the catalyst or something in it, the double bond, yes, this breaks. 1 electron, let's say, goes towards this side and 1 electron goes towards this side. Okay, similarly, the double bond in this also breaks. 1 electron comes on this side, 1 goes on this side. Now this electron which come on this side, this electron come on this side, they make a covalent bond with each other. Okay, so what is this? Now the double bond turned into single bond like this, and they have joined here, here. You see, these 3 molecules have joined together. You're not supposed to show this. I'm just explaining it. How the double bond breaks and 2 electrons on the both sides, they get connected with the neighbor ethene. And in this way, they keep connecting like this. So this was ethene. The molecule underneath is what? It is polyethene. This is what? Polyethene. But polyethene does not contain only 3 monomers. It contains thousands of monomers, right? So therefore, we clarify, we say it's a polyethene showing how many repeat units? Showing 3 repeat units. Okay, so we cannot show all the monomers or the repeat units, so we have to stop somewhere. So examiners usually ask you to draw the 1 repeat unit or maximum up to 3. Okay, so this is how the polymerization takes place. Now, if I put you to make a polymer from propene, look at this. Please stop writing. If this is propene, and if I ask you to polymerize this propene, what happens to this?
Double bond, one double bond breaks.
Here is the double bond. Okay. Now, first you have to put it in order. So what I'm going to do, I'm going to write the two carbons which are carrying the double bonds. First of all, okay, there are two carbons here which are carrying double bonds. So I'm writing it. How many hydrogens attached with it? The first one. So I'm going to put them like this. And what about the other one? Here, one CS. Okay. Now, what happens? As I told you, the double bond breaks and the both sides they extend. So now I'm going to write the same molecule without double bond because it is going to extend. So if it was propene, this is what? Polypropene, showing how many repeat units? At this moment, only one. If I have to draw, examiner asked me to draw the 3 repeat units, so I have to put them like this. Here is the third one.
सर जो फर्स्ट वन यूनिट में और सेकंड यूनिट में जो बीच में आप बॉन्ड बनाते हैं उसमें लेंथ आप बड़ी शो करते हैं तो सर
No, that's not the case. You just show them as normal, right? So that you do not have any such requirement. You just put them as you are. I can do this just to explain it. Okay, now look at this. How many repeat units? 1, 2, and 3 repeat units, right? Okay. Now at time what the examiner asks you, now they ask you to draw this thing in the semi-skeletal form. They don't use this word semi-skeletal, but they ask you to draw it like this. For example, this is CH, the first one. Look, what is this? The first one, CH. And who is next? CH2. So instead of writing it straight, I'm going to put it in a zigzag manner like this. And then who is next again? CH. CH2. You see? So same thing, that one, I have shown it like this. Instead of putting in a straight chain, in a zigzag manner. Now they ask you to draw at times the full skeletal. This is kind of semi-skeletal. They ask you to draw the full skeletal. So when they ask you to draw the full skeletal, you have to draw like this. You see?
So what does bracket show?
That is still continued. It is a polypropene showing how many repeat units? 3. So this is full skeletal 3 repeat units, semi-skeletal 3 repeat units, and this is a straight structural or displayed with 3 repeat units, right? And the examiners may also ask you to reverse it. Reverse means they can ask you, okay, this is the polymer having 3 repeat units. Can you find out what was the monomer for this? Can you find out? That's pretty much easy. You just have to take this slope out and put the double bond inside. Here is the slope and put the double bond in here. Got it? Again, and put the double bond. So you see it's the same thing. So you say it's a propene. All the monomers are the propene. Okay? Now I want you to give an example. For example, look. But 1-ene. So I want you to show the polymerization in butanene, and again you have to show three monomers joining together with three repeat units of polybutanene in all three forms: the semi-skeletal, skeletal, and the normal structural. Okay, here is butanene. So please draw it.
How many repeat units?
Three. Three repeat units, the structural, displayed, semi-skeletal, full skeletal. As I told you, first we have to write the two carbon having double bond. First carbon is having two hydrogens. Second one is having one hydrogen, and there is a CH2 and CH3. Now the double bond is gone. I have to write it three times. There is a hydrogen, hydrogen, CH2, CH3, hydrogen, 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 CH2, CH3, hydrogen. There is a hydrogen, hydrogen, CH2, CH3. Here it is. Is it like this? Okay, now in a zigzag manner, in a semi-skeletal, the first one is CH2, then CH. I'll put CH2, CH3 in the branch here. Then again CH2, CH. I'll put CH2, CH3 in the branch here. Again CH2, CH. And then CH2, CH3 in the branch here. Here it goes. Is it so? And then what about the full skeletal? Here. And then look at this. Once you go down, you have to take another turn. Here, once you go down, another turn. Here it is. Is it like this? Right? Now, if somebody asks you to take the monomer out, if they just show you this part of the polymer, they ask you to monomer out, you just have to cut the slope and put the double bond. Right? We'll continue this. We have more practice in the next session, next class. Right? Thank you very much. Allah Hafiz.